Hi, guys. So before we get started, is there any sort of procedural questions about the class? So I will remind you, today is the last day of homework. On Tuesday of next week, we will talk about two papers from the literature. The format of the class will be just like the class, like all the other classes. I'm still going to have a list of your names, only this time, instead of asking you to explain problem 3, I'll ask you to explain figure 3 and what's going on there. The papers are, I think for me, unusually short and should be easy to read. In fact, if all goes well, you will read both papers and say, duh, that was easy. God, I can't believe that got published as well as it did. And you will have discovered that at least in the 80s and early 90s, very straightforward applications of things you guys 100% understand now can get published extremely well and have large influences. It's maybe a little less true today, but it was certainly true not so terribly long ago. And then on Thursday, we're having an exam. And the idea is I would love for you guys to write out a sheet of paper, maybe front and back, that has all the formula you want to use for the exam. And on Thursday morning, I'd like you to send me a copy of that thing, and I'll send you a copy of the exam. And in an ideal world, the exam will take you an hour or two to do. It shouldn't take you much longer. But there shall be no time limits. You will hand it in when you hand it in. But I want all of you to sort of promise me you won't agonize over it. You won't fight it. You won't hurt yourself trying to figure out problems that are making no sense. If you're not making progress, give up and move on. And if the problem made sense, answer it fully. And when you're done, move on. Don't linger and fight. And for God's sake, you guys probably already know I'm not going to be taking off a whole lot of points for you dropped a 2 here, or you flipped a sign wrong here. I mean, that'll cost you a point for being careless, but it won't affect your exam grade in any way, shape, or form. If you get them all right and have little sign errors everywhere, oh my God, you'll end up with like a 95, and that'll be like an unbelievably good score. If on the other hand, about half the problems make sense to you and you get them right, yeah, that'll be about normal for the class. And so if a bunch of the problems are making sense to you and you're getting them right, and a few of them really just are weird and aren't making any sense, think, I'm kind of an average student. Okay, move on. And if they all make sense to you and you're blasting through them all, think you're really good at this. Think you're good enough at this that maybe you want to think about doing this for a career if it's fun. And that's why we make the exam as hard as it is. That it is supposed to be so that if they all made sense to you and you could all write them down really easily, you're good enough to do this for a living. And if you enjoy it, you should think about it. And if only the easy ones make sense, this isn't your career. And but know that you've learned an awful lot. Do I have questions about the exam or class structure or any of that stuff?
Can I actually ask a question about the last assignment, the
Oh,
problems
sure.
that we
Yeah.
offered? For question 2 in the past in assignment 6, I'm wondering why in the answer you showed us why is p hat 0 for edge like from 0.5 to 1, that range in the graph?
Yeah. Oops. Let's close that. If I had been sharing my screen, I would have been sharing a draft of the exam. So, all right, let me see. Oh, you guys don't. Once again, I've not turned on sharing for you guys, but now it is. All right. So this is a graph of h minus 1 over 2h minus 1. So let's look at the point, I don't know. Let's look at a point like 0.75. Plug it into your formula. So on the top, I have -1/4. On the bottom, I have, let's see if I can do this right in my head. I have 6/8 minus, 6/8 minus 1. What's that, like -1/2? So on the bottom, I have -1/4. On the top, I have -1/2. Well, I'm gonna have to write this down. Sorry. Let's do this. So on the top, at h equals 1/2 minus 1, that's equal to -1/2. And on the bottom, at actually, what did I say? I said I wanted to do this at, what did I say? Well, let's do it at 1/2. And at the bottom, that's just 0. So, but that's a singularity. That doesn't make the point as well. Let's do it at 3/4. 3/4 minus 1 equals -1/4. 3/4 times 2 equals 6/4. Minus 1 is equal to 1/2. So at the value 3/4, we would get -1/4 over 1/2, which is something like -1/2. But this is a value for the equilibrium frequency. So if the equilibrium frequency is -1/2, you know that can't possibly exist. There are a frequency of an allele has to be between 0 and 1. So since you know that that this can't be, you know that the equilibrium frequency doesn't exist, I've just sort of drawn it at 0, which is the point, which is sort of the closest point to what you got that is in the realm of existence. In fact, you know, it's actually going to go to 1 if the A1 allele is more fit, and it's going to go to 0 if the A2 allele, if the A2 homozygote is more fit. So if S is positive, the equilibrium frequency is going to be 1 across that entire range. And if S is negative, it's going to be 0 across that range. So if you've normalized it the way I've suggested, this actually should show that it's at 1 all the way across, or 0. Does that make sense? So those values, you can plug in values there, but you get values for P that are impossible, that don't exist, which tells you the equilibrium doesn't exist.
Yeah, that makes sense. Thank you.
Yep. Other questions about older problems? Well, you're with us, Julie. You were up first. I think as we left off with you with the
Sorry.
long Greenberg and Crow experiment.
Excuse me.
Yep.
Can I
Sorry.
interrupt
Yes.
before?
Oh, sure.
I'm
please.
sorry. I was just curious about problem 12 in the last homework, because like the way you solved it, it made like total sense, but I tried using the binomial and I got the same result.
Yeah.
For 12.
So let's look at my screen. So you say you wrote down 12 very explicitly as a binomial distribution. Is that what you said?
Yeah, just use the binomial distribution in R, just like as in, give me a second, D binom and between parentheses 0, 5, 0.23. So I use the same value for the probability and just like calculating the chances of getting 0 out of 5 trials, and I got the same value.
Yeah. So that's so if you look at my formula, right?
Yep.
It looks like 0.77 to the 5 power And you said 0.77 to the 5 power equals 0.77 to the 5 power times 0.23 to the 0 times 5, choose 0. So 0.77 to the 5 times the number 1 times the number 1 is just 0.77 to the 5.
I see it now.
So it was
Okay.
not a coincidence that that we got the exact same answer. We got the exact same answer because we used effectively the exact same formula. And the way I've done it is I've been thinking about it as if there was a whole lot of loci. There were m loci, and that the sum of this probability over a large number of those is 0.77. You said I'm going to approximate this as if there's a very small number of loci, and pick it about, but still, sort of really sort of approximate this as not a big number, but it's just as that to the 5, and it's not a. It turns. It's probably exactly equivalent to saying that the probability of 0 events in a binomial is equal to the probability of 0 events in a Poisson. No, it isn't. That isn't equivalent. It really is that we've both used binomials at some level here. I'm just hiding it a little better and using a lot more n's. If that makes sense. I think we're both used a binomial here when you sort of think about it. I've just used
Okay.
a lot more n's. But we had the same p, and the same, we had the same mean, and so therefore they got the same answer, effectively. Because this is almost like well, it's probably a 0. So if you use the same pn in a binomial, your probability of 0 is going to be the same. For any two binomials with the same NP, they have the same probability as 0, I think. That's what we've discovered.
Okay.
All right. Other questions about previous homework? Sorry. All right. You're up, Julie, with a bunch of algebra.
Sure. Okay. So for this question, we have this function, the 1 plus a times x over a plus x. And first we can plug in x into this equation, and the y value would be 1 minus x. So you just solve for x and to write x as a function of a and s. And then there's another point on the curve, which is 1 plus x over 2, and then the corresponding y value is 1 minus hs. And you put this x value into here, and then you do a lot of manipulations, and then in the end you would also write h as a function of a and s. And then I used the same a value as was used in figure 3.9, and then I plot this graph showing how h varies as s is changing to show the inverse homozygous heterozygous effect. So like when s is 1, so it's like a lethal mutation, and then the h value is something close to 0. But when s is about 0, it's how to say it? It's like h equals 0.5.
Yeah. Yeah. This is exactly what you're supposed to get. And you were supposed to get there through just nothing more than a bunch of algebra. That was done correctly here. Did anyone get any other values of algebra that they want to talk about or look at before we start talking about what this means? That was exactly the easiest algebra that.
I had a question.
Yes.
In the problem I think you provide, you said like x equals a1, a2 activity is 1 plus x over 2. So I thought I was supposed to put X into that equation. What is that? It doesn't seem like it's used for the answer. Why? What was that, and why was it provided?
So she did use it. Show where you use that, Julie.
It's used here. So 1 plus x over 2 is like an x value. And then the corresponding y value is 1 minus hs.
Gotcha.
So the let me see if I can. Does
I got all jumbled up.
that is yes. And now we're going to talk through this problem. So let's see if I still have the bootleg copy of John's book open. I do. All right. So let us start with John's bootleg, or bootleg of John. So we'll go back to Julie's solution. Keep your solution up, Julie, because we'll talk about it in a little bit, or I can put mine up, but yours was so pretty. So let's first talk about what's going on here. So this is sort of really, really kind of deep. And we did a bunch of silly algebra, but what we're trying to do is understand what is dominance. What is it? Why is it that a heterozygote is sometimes closer in fitness to one allele, to one homozygote? Sometimes it's closer in fitness to another homozygote. Why is dominance? It's a weird sort of question, a weird thing to think about. And Sewell Wright's answer for why dominance, why does it exist, is Sewell Wright says, I know about enzyme kinetics. At least I know as much enzyme kinetics as any other undergraduate does today. If you've taken first year biochemistry, you learn Michaelis-Menten kinetics. And what you learned from your sort of first year biochemistry is if you have any old enzyme, if on this axis, I plot the rate at which the enzyme works, and I'm in an organism like humans that have two alleles, almost always when I do this experiment, whenever anyone has done this experiment where I measure how well an enzyme works in a diploid organism, and there is variation in that enzyme, that individual, there's more than one allele, I find some individuals are homozygous and they have some level of enzyme activity. I find other alleles are homozygous and they have another amount of enzyme activity. And individuals who are heterozygous have half the amount of enzyme activity as well, 50%, sort of stuck halfway in between the other two homozygotes in enzyme activity. That a heterozygote looks very much like one allele is producing enzyme at one rate and the other allele is producing enzyme at the other rate. And therefore a heterozygote has exactly the average of those two values. So enzymatic activity looks additive. It looks completely linear. It looks like there is two alleles. You have two alleles. One homozygote might be high, another homozygote might be lower, but the heterozygote has activity 50% in between. Now on this axis, I'm not going to plot, although I have used the word, and John's used the word fitness, but because I'm a biochemist, I'm going to plot flux, sort of total flux through the pathway. What I'm looking at here is I'm imagining this enzyme is in a string of other enzymes, that I start at one end with glucose and at the other end I end up with ATP. And what matters is the total amount of ATP for the organism. What matters is say the amount of energy the organism has, not the amount of sort of one little thing converted to another, but I want to know how much product do I get out of that pathway as a result of the amount of input. And what I have found whenever I look at these sort of enzymatic pathways is the total amount of product that comes through the pathway tends to look a curve like something like this. And what is often the case is I don't necessarily need all that much enzyme to get enough product through so that this particular enzyme is not rate limiting. Something else in the pathway is. So unless the amount of product this particular enzymatic step is converting is very, very low, it probably has only a limited effect on the total amount of product through the pathway. And if I think this pathway is important for the organismal fitness, the most fit homozygote, well, it's from one fitness, the heterozygote who has activity halfway in between the two homozygotes will have fitness very, very close to the most fit homozygote, because even though this particular step in the pathway is producing product only half as fast as this is, I don't really need the full speed to get, because I'm being rate limited at some other step. However, if this step were really small, where I'm getting like really little product out of this step, this might be the rate limiting step, and the total amount of product I get out of the pathway might be quite low. And fitness, therefore, for this homozygote might be quite low. This shape is concave. And for any concave function, if you take 2 points on the sort of x-axis, the heterozygote, the point sort of halfway in between, will be closer to the highest point than it is to the lowest. Meaning if the shape of the curve that maps enzymatic activity onto fitness is concave, that will have the property that heterozygotes have an H less than a half. And it will also turn out that if the two homozygotes are close together, H will be nearly a half. Because if you sort of like pick 2 points on this curve that look close together, for if I pick a point here and pick a point here and go to the curve's going to look like a straight line in between them. Almost any 2 points I pick, if they're close together, the curve will look like a straight line, and the heterozygote will be halfway in between. The only way or close to halfway in between, the only way H is going to differ significantly from being halfway between a number like a half is if the points are very, very far apart. If one of them has almost no enzymatic activity and the other is sort of way out on the sort of flat part of the curve, then H will be dramatically less than a half, because the heterozygote will be much closer in fitness to the A1 homozygote. Does that make sense? So Sewell Wright's intuition is that the fitness function that maps enzymatic activity, that maps gene activity, is concave and looks something like this. And the reason he thinks that is he thinks this is some sort of like flux through an enzymatic pathway. And he believes most fitness functions are naturally concave on the scale of gene activity. And if we go back, so John plots this particular curve and he gives you that curve. So let's go back to Julie's screen. So let's go back to the top of this so we can see what we've done. So that first figure up here, this 3.9 thing, that 1 plus a times x over a plus x, John says is the actual equation for the graph he gave you. That's the equation. And he made that particular form of the equation just so that it looked like a concave fitness function. And the problem says to, if it sets x is the point near the sort of zero side, and it asks you to find the value of the y-axis, which is fitness, which Julie has correctly set to 1 minus s at that point x. And she did a bunch of algebra and showed that the value of x there is equal to a times 1 minus s over a plus s. And then the heterozygote, which is exactly halfway in between the value 1 and the value x, which therefore has value 1 plus x over 2, she has tried to find what that's the fitness function there. And she has solved for h in terms of a and s. So now, instead of looking at the plot of fitness versus enzymatic activity, Julie is now able to show us the plot of S, which is the difference between the two homozygous fitnesses, and H, which is the sort of difference between the heterozygote and the more fit homozygote. And she has produced this beautiful curve that shows when S is a value very near zero, meaning the two homozygotes are right next to each other, the curve looks nearly linear and H is about a half. Always less than a half because it's concave, but nearly a half. When S is a very big number, meaning the homozygotes are very far apart, H is a very small number, meaning the heterozygote has fitness much closer to the more fit homozygote. And the more you think about this, the more it will conform to everything you know about biology. That when there are, almost always, when there are alleles that tend to kill you, they are usually recessive, meaning H is a value very near zero. When you have alleles that tend to have, where the two homozygotes tend to have effect very similar to each other, the heterozygote tends to have an effect somewhere halfway in between. And you may not know that so well, but if you start looking at effect estimations for weak disease alleles in humans, you will see that not only are the effects so close, or H is so close to a half, almost everybody always assumes H is just a half when they do their sort of association statistical analyses, because it's so rare for it not to be, you might as well assume it. But not so much for these sort of Mendelian kind of diseases. All right.
Does that assumption get used in like experimental models or any kind of experiment when you're trying to figure out if a gene is like lethal, like, or when you have like rare genes or something like that, trying to figure it out?
You should.
Okay.
It
So it's
will
kind of like a
it
null.
will- Yeah, it will help your intuition, and it may help your experiment planning a lot if you assume it. Now, that is not to say there are not alleles that do have large effect as heterozygotes. They're very, very rare. In human geneticists often give them strange names, like dominant negative. Like it's like they encountered it so rarely, they started thinking about it like a weird thing. But it's really just H equals 1. I mean, it's an allele where S is large and H is bigger than a half. It's not common. It's not, the fact that inbreeding depression exists tells you it's not common at all. It's very rare for that to exist. Everything we know about nature tells us already that H is less than a half on average. So we shouldn't plan on looking for these sort of dominant negatives, but they can exist, and there are many examples of them.
So can you take this kind of intuition and probably with a bit more math, but does it extend to why a lot of people think that variance for, polymorphic traits is additive as well? I mean, to me, I feel like there's a connection here somewhere between this and that. But
The connection will be made as explicit as you can possibly imagine in homework 9.
got it.
In homework 9, we will partition the effects into what they should have been had the locus been perfectly additive, and then think about the difference between what the effects truly are and what they would have been had they been perfectly additive. And we will then start asking questions of, can we measure how far the observation is from what it would have been had it been perfectly additive? And the answer is, usually you will be able to detect departures from perfect additivity, but they will not constitute very much of the variation. In the toy problems I give you to teach you how to make the calculations, they might be huge. It might be all dominance effects. But in anything that had a number that looked like it came out of nature, you will find there is almost no evidence, maybe a little bit, maybe 5–10% of the genetic variation that looks like it departs from h equals a half. And the additivity, the additive variance, and h equals a half at a locus are the exact same thing. Like they're the same concept. And you'll even every now and then hear, like someone like me just randomly switch between the word dominance and h and additive and a half, and like they are so deeply fundamentally the same thing that that you can think about it as departures from h equals a half, or you can think of it as departures from a linear regression, or you can think of it a lot of different ways. But they're all fundamentally deeply the same thing. And the fact that you will know or you will learn that most variation is additive will turn out to be even more evidence that h is almost always nearly a half. But it must be less than a half, or mating with your sister would be good for you. So it's the fact that we know close relatives tend to produce offspring that are not as fit as random mating suggests h is on average less than a half. Other questions? Okay, is Michelle with us? She's up for the next problem before we circle around.
All right, I'm
Yeah.
here. Okay, so we're on 14.
Yeah.
Okay, so 14 is we have a changing environment and we're giving the fitnesses for some genotypes. And the question is, what is the mean fitness of the 3 genotypes? So Gillespie gives us
Oh,
this.
wow, look at that. You've done a geometric mean. I was just looking for the first part of what you've done here.
Okay, well, arithmetic mean is super easy to get, and it's basically just 1/4 times all of the fitnesses added up.
Yeah, absolutely. So so there is some history here. So the first person to ever examine fluctuating environments was in the 50s, and God, I can't remember his name. It's not very far from Bruce's name. It's like a Don Levine or something. I can't remember. But anyway, he was the first person to show that in the model of fluctuating environment that he got, what mattered ultimately was the geometric mean fitnesses. And he came up with a whole bunch of rules for this particularly narrow model of fluctuating environment that compared geometric mean fitnesses. And he also developed some intuition for why geometric mean fitness would matter most. Gillespie, years later, when he started doing his PhD and after, he cleaned up a lot of that thinking and extended the models much more broadly. And really, it turns out that the reason geometric mean fitness mattered so much was because geometric mean fitness really can be approximated by the first few moments of the fitness function. And that you can actually, most of the results you can obtain, you can obtain by comparing the first moment, the arithmetic mean, and the variances to each other. And for a very, very broad collection of changing environments, you should probably think of the easiest way to think of polymorphic conditions. Really, it's not so much in terms of geometric mean fitnesses, but really just as invariances in the first sort of the usual moments we're used to thinking about. So there's a bunch of stuff in there that about geometric means that is in there for historical purposes, because you can prove it's exactly right in very simple models. But more broadly, these sorts of conditions will be most important, where the mean is relative to the variance. And so for this, I just was asking to calculate the arithmetic mean, the first moment, the first expectation. So absolutely perfect, great. So let's cycle around. We have a new day, and Kiana, you're up first with the next problem, which also should be super simple.
Okie dokie. So that's problem 15, correct? The variances?
Yeah.
Alrighty, let me share my screen. Okay, so for this, I used this formula for variance, where it's the expected value of x squared minus the expected value of x quantity squared. I used the same means, E of W, I, J, from problem 14, and then I calculated the expected value of W squared similarly, where it was PI, which is 1/4 times XI squared for each of them summed. And then I plugged in, chugged, and I got these values of variance.
Yep, absolutely. Totally correct. 100% correct. And it should be perfectly intuitive to you guys why the variances of W11 is equal to the variance of W22. It's because John picked the selection coefficients, or I picked the selection coefficients, so that one of them looked like 1 plus a random number and the other looked like 1 minus a random number. So you will remember that the variance of a constant plus a random variable is equal to the variance of just that random variable. And if I multiply a random variable by a minus sign, that comes out as a square. So it looks, so the variance of a constant plus a random variable is equal to the variance of a constant minus the random variable. So if you construct your fitnesses so that one of them is plus S and one of them is minus S, for sure, the variance of one of the homozygotes is going to equal the variance of the other. And the thing in the middle, we just set equal to 1. So and of course, this variance is also going to equal the variance in that S term, because that's just what you learned first week. All right. So what we've seen in problem 14 is that one of the homozygotes had mean 1.05. Another homozygote had mean 0. The last homozygote had mean 0.95. If the environments were not changing ever, you would imagine this is directional selection. This is H equals a half. A1 has fitness 1. A2 has fitness 0.95 over 1.5. This thing has fitness HS. H is a half. S is something or other in here, about 0.1. You would say this is directional selection. The A1 allele is going to fix. for sure. And your intuition is the A1 allele is going to fix if the way the world works is the A1 allele has enough time to increase to reach fixation before the environment changes on it and it starts going in the other direction. So your intuition is that polymorphism ought to go away. It ought to behave just like directional selection unless an allele doesn't get a chance to follow a path for very long. It goes up and then suddenly it starts coming back down again. And it goes up again and suddenly starts coming back down. It starts going back and forth rapidly. And what's measuring the speed at which it's changing directions is really the variance. Sort of the speed and the strength of the direction change is really the variance here. So it will turn out that if the difference in means between the two homozygotes is large relative to how fast it changes, then it's directional selection. However, if it changes a lot relative to how fast it moves on average, you'll maintain polymorphism indefinitely. And since you wanted to show it to us anyway, let's go ahead and finish this off, Kiana, and show us whether or not
you're talking about it. I don't.
Yeah. So the condition turns out to be that the difference in means is less than half the variance. That's sort of the approximate formula. If the difference in the means, in the mean fitness between the two homozygotes is smaller than the variance, then polymorphism will be, or the variance over 2, then polymorphism will be maintained. There you are. And for large classes of models, the maintenance of polymorphism condition is the difference in means is less than a linear function of variance, C. And that John made his career about writing down model after model and finding the value of C that will allow variance to be maintained. And all of those models had the property that fitness was a concave function, was a convex function, and that on the x-axis the effect was additive, but the fitness function was concave. Those classes of models have a name or are called by a few people concave fitness function stochastic additive scale. Those Sasquiff models, stochastic additive scale concave fitness function, are really sort of a set of mathematics that allow you to analyze almost any kind of fluctuating environment that has the function that has a property that it maintains fitness in a concave function. And the reason to restrict yourself to those is A, they occur in nature, and B, any other condition will generally not maintain polymorphism. Any other shape of the fitness function will probably leave you screwed, and it'll just be directional selection. That'll be your intuition if you get into this stuff. All right, is that the end of the homework?
So for this formula real quick, just reminding me I missed it, but if it was the other situation where the difference in the means was greater than the variance over 2, that means one of the alleles would fix, and whichever one had the greatest average would?
You've got it.
Okay.
100%, that's it. That's your intuition. That, of course, the more fit average allele ought to fix. That ought to be the dumb intuition. That's the intuition every reasonable person you will ever meet will have, and they're right. It just turns out if selection fluctuates fast enough or large enough that you could maintain polymorphism for arbitrarily long periods of time. So the intuition is it ought to fix to the more fit allele on average, but it doesn't if the variance is big. And you guys, because we did homework 1 in utter absurd painfulness, you now fully understand how boring the concept of mean and variance is. They are not deep, they're not hard, but they're deep in the sense that one of them is measuring averages, what's going on average, and the other is measuring how much variation there is. And the relationship between the two will probably give you everything you need to know about a system, or at least give you a lot to understand about a system that's evolving over time. And that's it for homework 6. And that is it for everything that is on your exam. Expect all of the questions to come from the homework, or possibly from the readings next week. But the readings next week, you will see, came from your homework. There is nothing about those readings that you have either not already done or you could have done if someone had asked you to, because they're really simplistic ideas that actually have some somewhat powerful results. And at this, we'll do a little more with selection a little bit after the exam, but not much. And then we'll start moving into sort of more 2 locus models and maybe a little bit of population structure and stuff like that before we go full on quantitative genetics. Anything you guys want to talk about right now?
I don't want to like overbear, but I was just actually wondering if we could talk just very briefly again about 15 and why the 2 values are equal to each other. I just didn't quite get it in your explanation.
Yeah. So let me see if I can. It probably would have been better, like if sometimes not having a blackboard is a bit of a thing. So fake Gillespie. So he doesn't even bother to construct them in this fashion exactly. Oh, well, he didn't do it that way. No wonder this made no sense to you. All right, let's look at, I thought John presented it this way. He doesn't. It's just the way he had presented on the blackboard. Okay, so are you, God almighty, this is asinine. Can you see my screen right now?
Yep, I'm looking at the beginning of problem 14.
So in problem 14, I said there are 3 genotypes, and a quarter of the time they're in these sort of different states. And I constructed it, and I didn't tell you I did that, by making the heterozygote always have fitness 1. And then I made one of the homozygotes have fitness 1 plus S. And I made the other homozygote have fitness 1 minus S. Because I thought that's how John did it in the book. I haven't read this book in 30 years. This is how he would have done it on the blackboard. Is he would have constructed these fitnesses as 1 plus S, and 1 minus S. So this is 1 plus S, 1 minus S. This is 1 plus S. This is 1 minus S. 1 plus S, but S is minus a quarter. So this is plus a quarter, minus 0.7, plus 0.7. So when I was making up these numbers, I made them up so that for sure, these two things were always having the same mean change and therefore always the same variance change, because this was 1 plus a random number. This was 1 minus that random number. And so so I could have talked about the distribution of the thing that generates that that random number. And it turned out the thing that generated that random number had mean 0.1 and variance 0.38. So if you were just looking at the random number generator itself, the condition for polymorphism is, again, the mean of the random number generator is less than half the variance. That's what I had in my head. That's how I was constructing this scenario. And that's, which is why these two things end up with the exact same variance. And
Gotcha.
And in John's constructions of the problems, they are also have that structure that deeply it really is that he's thinking about the random quantity as being applied equally to both sides, which is why it's stochastic additive scale. The heterozygote is going to be halfway in between the two of them.
That makes sense, because it's like if you were to graph it, you would you'd be shifting the shape, but not necessarily, or you'd be
Exactly.
variance. Yeah, you're just shifting the shape, but you're not like narrowing or widening it.
If you move the mean, you can make for big differences without if you don't make the curve fatter, then you're going to change what happens ultimately. Other questions? Okay, so honest to God, if you get nothing out of this class, like you walk out and you don't remember anything, try to remember that on average, almost always, the heterozygous effect is going to be less than a half. That the heterozygote is going to have an effect closer to the bigger, more homozygote, more fit homozygote. H is almost always going to be less than a half, but barely less than a half if the effects are small. That H is almost always a half if the effects are small. And if the effects are big, H could be close to 0. So that the heterozygote really is just like the more fit homozygote, and the other homozygote is kind of bad. If you have that intuition, so much of what you see the rest of your life will make sense. Every GWAS study you ever look at will make sense. All they're detecting is small effects. You already know if S had been big, if HS had been big, the allele frequency ought to be tiny. Q hat ought to look like mu over HS. So if the effects are big, the allele frequencies ought to be tiny. That's what mutation selection balance is telling you. So if the allele frequencies you're looking at are large, H is almost surely a half. Almost has to be. Not always. But if you start with that assumption, the world will make much better sense to you than any other way. Other questions? Okay, so next Tuesday, we're going to look at null alleles in flies and try to learn something about heterozygotes of null alleles from the frequency of which they occur. A null allele, by the way, is a broken enzyme, a broken protein. It's something that does not work. So, and the year is 1980. The vast majority of enzymes we know are really, really important. Like they're the Krebs cycle stuff. They're like blood. And null alleles would tend to be thought of as very bad things in homozygous state. And but they exist in nature, and we're going to learn something about that. And the other paper is one of the most prominent tests of natural selection out there, a McDonald-Kreitman test, which you will see is about as obnoxiously simple as anything out there. And you will understand it. You will be able to prove why it is. It's nothing. And but works kind of good. You can reject neutrality a lot with it. And then the exam for Thursday. Any last questions? So obviously throw me any question you like over email, and I will try to answer it over email. If it is something too difficult to answer over email, we can try to set up a Zoom to get your questions answered before the exam. Know that if I've written the exam correctly, it can be finished in under a half hour. That it's not going to be this problem. Well, maybe this one. This one's actually pretty quick, but it's not going to be this problem for sure. And if you were tending into this area, it has gone off the rails for you. And there may be many steps to the problem, but the problem should be, each step should be very quick and easy. And I'll give it to you on Thursday, and you can hand it in whenever you like. But please don't fight it. Just let it be. And if it's going great, send me a great exam. And if it's not going great, send me the ones that went well for you. Any last questions? Okay. Somebody has something in chat. Let me make sure. I will see you guys all next Tuesday.